Okay, so this week we're going to learn about how to work word problems with these mighty z-scores. We are going to work all of these problems together, and then in your homework and on your quiz, you'll be working some of the same kinds of problems all by yourselves. I want you to read this first problem and then pause the video. I want for you to get into the habit of stopping the video before someone tells you the answer and working through the problem yourself to see what you know and what you don't know. Sarah is 5 foot 2 inches tall. She just wants to know her percentile for her height. 5 foot 2 is 62 inches. And the z-score, x minus mu over sigma, would be 62 minus 64 divided by 3. 64 is the average height for women, and 3 is the standard deviation. That equals minus 2 over 3. It's a minus because Sarah is shorter than the average of 64. And minus 2 over 3 is minus 0.67. So Sarah's z-score for height is minus 0.67. A percentile is the percentage of scores that occur below the z-score. So we need to get the z-table and find her percentile. So we can see from the z-table that in the body of a 0.67 is 74.86% of the scores. So z is minus 0.67, and the percentile is the percentage of scores below z. From the table, we find that the proportion of scores in the body of a positive z-score, 0.67, is 0.7486. So 74.86% of the scores are in the body of a z-score of 0.67. And 74.86% is also in the body of a z-score of minus 0.67. So if we take 100 and subtract the body, 74.86, we get the percent in the tail, 26.14%. And if 26.14% are in the tail of a z-score of plus 0.67, then 26.14% is in the tail of a minus 0.67 as well. So she's in the 26.14 percentile of height. Read this, pause the slide, and try to work it yourself. So we need to know the percentage of scores that are in between Joe's IQ test and his reading test. And if 50% of scores are in between those two test scores, then the teacher's going to send Joe to be evaluated for a reading disability. And the first thing we need to do is find Joe's z-scores. So for IQ, Joe's score is 105, the mean is 100, the standard deviation is 15. The z-score is 0.33. And for the reading score, Joe's score is 45, the mean is 50, and the standard deviation is 10. And the z-score is minus 0.5. We need to find the area between those two z-scores, between minus 0.5 and 0.33. And in order to find that, we need to find the body, the percentage of scores in the body of a z-score of 0.33, and then subtract off the percentage of scores in the tail of a z-score of minus 0.5. So let's remember, we need the body of a 0.33 and the tail of a minus 0.5. But the z-table only gives us a body, and we're going to have to figure out the tail of the minus 0.5 from the body. So I see that the body of a 0.33 is 0.6293. So 62.93% is in the body of a 0.33. And in the body of a minus 0.5 is 69.15%. So now we need to find the area between a z-score of minus 0.5 and a z-score of 0.33. We've already found the percent in the body of a 0.33. That was 62.93%. And we found the percent in the body of a minus 0.5. That was 69.15%. We need to find the percent in the tail of a minus 0.5. And to get the tail information, we just subtract the body information from 100, from all of the scores. 100% of the scores minus 69.15% is 30.85%. So there are 30.85% of the scores in the tail of a z-score of minus 0.5. To get the area between, the percentage of scores between two z-scores, we take the z-score with the larger percentage, so the z-score that corresponds to 0.33, which had 62.93% of the scores in the body, and subtract off the tail of the 0.5. And when we do that, we get 32.08% of the scores are between two z-scores of minus 0.5 and 0.33. In order to be assessed for a disability, at least 50% of scores have to be located between Joe's IQ score and his reading score. But only 32.08% were located there. So should Joe be evaluated for a reading disability? No, because 32.08% of the scores is less than 50% of the scores. Take time to read the word problem and try to answer it yourself. So we need to find the cutoff that divides this distribution into the top 20% and the bottom 80%. The z-table is going to give us information about the body. The z-table will give us the z-score that's associated with 80% of the scores in the body. It looks like 79.95% of the scores is about as close as we can get to 80% of the scores. And for that number, a z-score that's associated with 79.95% of the scores is 0.84. So we know that a z-score of 0.84 corresponds to 80% of the scores in the body and 20% in the tail. But she wants to know what score separates the top 20% from the bottom 80%. So we need to convert that z-score into an x. And we have all the information we need. And we know that mu for study skills is 10 and sigma is 1. And the formula is x is equal to z sigma plus mu. So x is equal to 0.84 times sigma, which is 1, plus mu, which is 10. And we get 10.84 is the test score that is the cutoff for the top 20%. Read the problem and try it on your own. The first thing we need to do here is figure out what percentage of people she wants in her study. She only wants 100 of the 800 people. And so that's only 12.5% of the people in nursing homes that she has access to that she wants in her study. So if we're looking for 12.5% of the least depressed people, we need to go to the z-table to find out what z-value that corresponds to. If we have 12.5% of the z-scores in the tail, then we have 87.5% of z-scores in the body. And the closest I can see is 0.8749. which corresponds to a z-score of 1.15. The z-score associated with having 12.5% of the lowest scores and 87.5% of the higher scores is minus 1.15. So we need now the score that's associated with a z-score of minus 1.15. And we know that the formula is z sigma plus mu. So we take z minus 1.15 times sigma 10 plus mu 60 and the cutoff score to find the people, 12.5% of them who are the least depressed, who will be 100 people in her study. The cutoff score is 48.5. Okay, read it, stop the video, and try it yourself. Okay, this health psychologist wants patients who are at risk for suicide ideation. And she wants to know how many people she's going to have in her study if she recruits all the people who were at risk. We need to find the z-scores associated with a score of 120 and 130, and then we need to figure out what the area between those two z-scores is, the proportion and then the percentage of people between z-scores associated with scores of 120 and 130. So we can find the z-scores easy enough. I get a z-score of 1 for 120 and a z-score of 1.5 for 130. And now we need the table. So for a z-score of 1.5, I get 93.32% of the scores in the body. And for a z-score of 1, I get 84.13% of z-scores in the body. So we need to get the area between z-scores of 1.5 and 1 in order to turn that into a number of people. It looks to me like if we get the body of a 1.5 and subtract off the body of a 1, what will be left is the percentage of scores between a 1.5 and a 1. And that's what we want. So I get that if the body of a 1.5 is 93.32 and the body of a 1 is 84.13, and we subtract those to get the between area, I get 9.19%. Which if we multiply the proportion 0.0919 times 500, we get that that's about 46 people she will have in her study that qualify for her counseling program. Read the scenario and work the problem. This teacher has been told that she needs to grade on a normal curve. So we need to find the scores that separate an A from a B from a C, and so on. And in order to do that, we need to find z-scores that correspond to the percentage of scores under the distribution that she has to comply with. So, from what I can see, if an A can only be 10% of the top scores, then 90% of the rest of the distribution is either a B, C, D, or F. And if we turn that around, if an F can only be 10% of the distribution, the lowest part of the distribution, then 90% of the distribution is in the other direction, D, C, B, A. And if 20% of the scores have to be a B, then it has to be the case that the rest of the scores, exempting the A's, because we've already considered them, are C's, D's, and F's. So it must be that there are 10% of the F's and 20% of the D's and 40% of the C's that are on one side of the distribution in the body, and the 30% of B's and A's are on the other side in the tail. And since this distribution is symmetric, we only need to find the cut for AB and BC because it applies to CD and DF. So now we need to go to the z-score table. So the closest I can come to 90% of the scores in the body is 0.8997. And the z-score looks to be 1.28. 1.28 has 90% of the scores, or real close to it, in the body. The z-score associated with 70% of the scores in the body is 0.52. So we learned from the z-table that 1.28, the z-score of 1.28 separates 10% of the distribution in the tail from 90% in the body. And that for us is going to separate an A from a B, and a minus 1.28 will separate an F from a D. We also learned that 0.52 separates 30% in the tail from the other 70% in the body. And for us, that will separate a B from a C and also a C from a D. So what's left is to turn those z-scores, 1.28, 0.52, minus 0.52, and minus 1.528, into raw scores with a mean of 50 and a standard deviation of 10. And that's just applying the formula that gets an X from the z-score, mu, and sigma. And here's the final answer. Okay, last one. Try to work it on your own. Okay, so I saved the easiest one for last. All we're trying to do here is take Stan's SAT score, figure out what the z-score is for his SAT score, and then turn it back into an X value, a score, but in ACT terms. So we find the z-score for SAT. Stan's SAT score is a z-score of 1.04. And when we turn that back into a raw score with the mean and standard deviation of ACT, we get a 26.2. So Stan would have scored a 26.2 on the ACT if he had scored in the same percentile as he did on the SAT. And one more thing. So this normal curve is not only used to find the proportion of scores here and there, it's also used to detect when scores are aberrant. Outliers don't belong to the distribution. Scores that look different from the rest of the scores. Usually people do that at these percentages, 95%, which corresponds to z-scores of plus or minus 1.96. So 95% is in the body and 5% of the distribution is in the tail. And z-scores that are beyond the 5% are considered aberrant, not belonging to the distribution, outliers. Sometimes we use the 99% cutoff. If we really want very few of the scores, only 1% of the scores, we're going to say don't belong to this distribution, then the 99% cutoff will be used.